Welcome back. Now, before we delve into a little bit more mathematics of this, what we want to take a look at is the technique that is typically used to measure the heat transfer processes and reactions that we're looking at. And so heat transfer is measured by the technique calorimetry. It's where we get the word calorie from, and vice versa. We don't use calories as much anymore in science, but we will see in a moment that a calorie that is a food calorie is 1,000 calories. So a food calorie is 1,000 calories, and 1 little calorie is 4.184 joules. So it gives you some perspective of what we're measuring here. Now, in order to do this, we need an insulated container. We want to somehow isolate the system and its immediate surroundings that we will be measuring the changes in, or the immediate surroundings, and we want to isolate that from the rest. So we want to kind of keep these isolated from the rest of the world, so to speak. Now, there's two ways that this is done. This can be done at constant pressure or at constant volume. If it's constant pressure, delta H is equal to Q at constant pressure. If it's constant volume, that equality doesn't hold true, and I'm not going to get into that at this point. So let's take a look at the next slide. This is a picture of a calorimeter, and it gives us the components. This is a particular type of calorimetry. It's a constant volume bomb calorimeter, and it is used for measuring combustion reactions. So we'll add oxygen to a reactant, and so we need a pure oxygen source, and we isolate the system in this container here, and we're going to provide a source of pure oxygen into that. Now, a combustion process is exothermic. Hopefully that's self-evident to you. It's going to give off heat, and that heat's going to go one of two places. It can go to the water. This would be water in here. Water has a high heat capacity, so it can absorb a lot of water without changing temperature. Or heat could actually be absorbed by the calorimeter components itself. Now, hopefully, if it's insulated well, we're not losing heat outside of our calorimeter. And at this level, we're actually going to neglect the heat absorbed by the components of the calorimeter, and we're going to focus only on that which is absorbed by this large amount of water. Now, the other components include a thermometer, a temperature probe, a stir, because we want to keep it well mixed to have the smooth process of transfer of heat energy, and the wire to ignite, because even though it's exothermic, every reaction has to overcome a minimum energy called the activation energy. And we're going to talk about that activation energy in a little bit more detail in the next unit. So, oxygen would be put in here. It would be ignited just to initiate the reaction. Doesn't need to be added heat continuously to keep the reaction going. We just need to initiate it. Then the heat's going to leave and be absorbed by the water, and we're going to look at the temperature changes in the water. What that means is that the heat lost by the system is going to be equal and opposite in magnitude to the heat gained by our surroundings. Equal in magnitude, opposite in sign. Now, I'm not saying this will end up being negative. All that means is it's going to be the opposite sign. We still could have positives and negatives here in the end, but we have to see that whatever is lost here is going to be gained here, so they're going to be equal magnitude and opposite signs for that. Now, we're not going to be doing one with this type of a bomb calorimeter. They're a little expensive for our ability to pay for here. And hopefully we're going to be able to pull this one together for you. Actually, there are two we're working on for you. And this would be a simple constant pressure. It's just open to the atmosphere combustion process. And we're just going to take a little bit of a food item here, and we're going to surround it by another container that we hope will hold in heat. As you can see, the likelihood of this happening is not all that high, but we'll hope it holds in heat. We're going to ignite the food. The heat given off is going to go into the water, and then we're going to put, oh, that was a lovely glitch. We're going to put a little thermometer in here. Love my drawing, and we're going to measure the temperature with that thermometer. Now, by looking at that change in temperature, we can use this equation that Q of combustion of our Cheez-It or our Cheeto or whatever we're going to do there is going to be equal in magnitude but opposite in sign to the water. And that assumes no loss anywhere else. No loss to the rest of the surroundings. And I will let you be the judge of whether you think that's a reasonable assumption or not. But it is a fun little lab. Now, the other thing that we can do for these is use what's called a coffee cup calorimeter. We will definitely be doing this if you take the advantage of AP Chemistry in your senior year, junior or senior year. And we're actually going to be doing a short one, just a small one, in pre-AP Chemistry. So here we're going to use a thermometer or a temperature probe. In this case, we're going to be doing a neutralization reaction or a dissolving. So often it's dissolving or neutralization. Some sorts of reactions like that. Maybe the metals reacting with water, magnesium metal reacting with water. And believe it or not, these two Nestle styrofoam containers really do block quite a bit of heat. So that really we only have to worry about heat going from our system, which is the point at which bonds are breaking and bonds are forming. So there's it's a very fuzzy boundary between the system and the surroundings here. So the system is right at that point that bonds are broken or being formed, and the surroundings become two possibilities. We have the bulk solution, and we have the calorimeter itself. Now in AP Chemistry, we're going to include the calorimeter in our conversation. In pre-AP Chemistry, we're going to neglect this component. So again, we get the type of equation that Q of our process, our reaction or our process, is going to be equal in magnitude but opposite in sign of Q of my bulk solution. So if our reaction releases heat, the solution gains heat. If our solution needs to gain heat, it's going to pull it or reaction needs to gain heat, it's going to pull it from the solution. So equal magnitude, opposite signs. And this is surprisingly a good little calorimeter. We get pretty decent results with this. Now, we've talked about this. Let's summarize a few things. The basic idea of a calorimeter is to capture the heat released. We're going to capture that heat released typically in some sort of reservoir or water. That reservoir could be the bulk solution of an aqueous reaction. So the bulk solution. We measure the temperature. At the beginning, you measure it at the end, and we're going to use MCAT. And we get to make the assumption that no heat was lost by the calorimeter, and it was all in the water. So heat loss by the process is equal in magnitude but opposite in sign. So that's why that's a negative sign right there. So we're going to look at some of those formulas, but it's pretty much just doing the same thing we've done before. We're going to be doing a lot of MCAT calculations. We just need to watch our signs. And the best way to make sure you have the right sign is to use your logic.